All right, today we're going to crack open one of the most important but maybe least known black boxes in all of modern technology. I'm talking about the operational amplifier, the op-amp. It's a fundamental piece of pretty much everything electronic. And its story? Well, it wasn't born in some Silicon Valley garage. Nope, it came from the intense pressure of war and the amazing vision of one single engineer.
You know, before our nice, clean, predictable world of ones and zeros, of digital, engineers were locked in this visceral struggle with physics itself. It was the golden age of analog. I mean, they were literally wrestling with the infinite shades of the real world, things like sound, temperature, light, and trying to somehow tame the chaotic flow of electrons to make any sense of it all. It was a whole different ballgame.
So, let's really break this down. You can see the two worlds engineers were trying to connect right here. On one side, you've got the analog world. It's a continuum, right? It's reality in all its messy, complex glory. And then on the other side, there's the digital world we all know and love. So clean, so abstract, just ones and zeros. The challenge for those early pioneers was to build a bridge between them, to somehow translate all that messiness into a language that electronics could actually work with. So where did this incredible bridge come from? You might think, maybe for high-end stereos or cool music synthesizers, but no, not even close. The idea was actually forged in the fires of World War II. It was born from a desperate life-or-death need for precision on the battlefield. And the challenge was? Well, it was immense. Just think about it for a second. You're trying to aim an anti-aircraft gun. You need to calculate, in real time, the exact path a shell needs to take to hit a plane that's screaming across the sky. A human? By the time you've done the math, the plane is miles away. They needed a new kind of electronic brain, something that could do incredibly complex calculus faster than any human ever could. And that's where Bell Labs came in. They developed these amazing things called electronic analog computers. A great example is the M9 gun director. It used a whole network of vacuum-tubed amplifiers to crunch radar data and spit out those life-or-death calculations, like instantly. It was this incredible feat of real-time calculus, and it saved so many lives, so many aircraft. And the secret sauce to all of it? It hinged on this one key principle called negative feedback. Now, this didn't just appear out of thin air. It was a journey, and you can see the whole thing laid out here. It's pretty fascinating, actually. The core theory of negative feedback, that was worked out way back in the 30s. Then, in 1941, a key part of the circuit gets patented for that gun director we just talked about. But it took until 1947 for a guy named John Ragazzini to finally put a name to it. He called it the operational amplifier. And here's the key takeaway, the really crucial point. An op-amp wasn't just about amping up a signal, making it louder. The clue is right there in the name, operational amplifier. It was designed to perform mathematical operations. It was this incredibly flexible, powerful engine for doing math in the analog world. Okay, but here's the thing. These first op-amps they were monsters. Huge, power-guzzling beasts locked away inside these giant, top-secret military computers. It really took a true visionary, an engineer who could look at that incredible military tech and see its potential for, everybody else. And that visionary's name was George A. Philbrick. This guy was brilliant. He'd worked on flight simulators during the war, so he knew exactly how powerful this technology was. So in 1946, he starts his own company, George A. Philbrick Researches, or GAP-RS for short, with just one mission in mind, to get the op-amp out of the military and into the hands of every engineer out there. And his big moment? It came in 1952 with this, the K2W. The comparison to the Ford Model T is just perfect. It wasn't the first car, right? And the K2W wasn't the first op-amp, but it was the first one that was mass-produced, affordable, and standardized. And just like the Model T, it absolutely changed the game for everyone in the field. And the price? Get this, about $22. Now that's a bit over $200 in today's money, but think about what it meant. Any engineer, any university lab, even a hobbyist tinkering in their garage could suddenly buy this reliable, super versatile, off-the-shelf black box of gain. I mean, the power of analog computing was basically democratized, like overnight. So, what was the big deal? What exactly made this little black box such a revolution? And how did it take those early military ideas to the next level? All right, let's pop the hood and take a look inside.
So on the outside, it was pretty clever. It was designed to look familiar, plugging right into a standard 8-pin socket, just like any old vacuum tube. But inside, that's where the magic was, this really elegant circuit built around 2 tubes. But its most important trick, the real key feature, was its differential input. Basically, it let the op-amp amplify the difference between 2 signals while totally ignoring any noise that was common to both of them. It's a game-changing idea that is still used in every single op-amp today.
Okay, but one of the most clever things about it was how it solved this really fundamental problem. See, vacuum tubes run super hot, on hundreds of volts of power. But the output signal, the useful part, needs to be hovering right around 0 volts. So what did Philbrick do? His solution was just ingenious. He used 2 simple neon glow bulbs, like the kind you'd find in an old indicator light. They acted like a perfect little floating battery, dropping the voltage down to exactly where it needed to be. It's just beautiful, a real mark of engineering artistry.
Now, looking at the specs today, you might kind of laugh. I mean, it needed a massive plus and minus 300 volt power supply, it drank power, and it got hot. But you know what? None of that mattered. Its impact was just undeniable. Suddenly, engineers didn't have to spend weeks painstakingly designing a custom amplifier for every little job. They could just grab a K2W, plug it in, and get right to work on the actual problem. So yeah, the K2RU really established the op-amp as this modular, off-the-shelf part. It totally changed how people designed circuits, and it was a peek into the future, a future of integrated circuits. But the reign of the vacuum tube, its days were already numbered. See, the transistor was actually invented just a year after Philbrick started his company. But the switch didn't happen overnight, not at all. Early transistors were, well, they were terrible. They were notoriously unreliable, super noisy, and would go haywire if the temperature changed even a little bit. For the kind of high-precision analog stuff op-amps were built for, they just weren't ready for prime time. But by the time the late 1950s rolled around, things had changed. Silicon transistors got way, way better, and new companies started popping up to challenge Philbrick. A great one is Burr Brown, famously started in a garage in Tucson, Arizona, and they began making these smaller, solid-state op-amp modules. They basically just packed a bunch of individual transistors into these little blocks of epoxy. And you can really see the evolution here. I mean, these new solid-state modules were a huge improvement. They were smaller, they used way less power, and they ran so much cooler. But there were still these complex little things that had to be assembled by hand. So this was a really important step in shrinking that black box, for sure. But it wasn't the final revolution. That would have to wait for the integrated circuit.
So, when you boil it all down, what's the real lasting legacy of Philbrick's K2W? It's this. It completely changed how engineers thought about their jobs. It proved that you could take a really complex circuit design problem and package it up into a simple, reliable, reusable block. It introduced the entire world to the power of modular abstraction.
You ever stop and think about how we got from computers the size of a room to the phone that fits in your pocket? Well, it all kicked off with a crisis. A problem so huge it almost stopped the computer age cold. And it led to this incredible invention that, let's be honest, now powers our entire world. So how did it all go down? Here's the roadmap for our story. We're going to start with what they called the tyranny of numbers. That's the crisis I was just talking about. Then, we'll look at the very first idea on a chip, the revolution that actually made it practical, the wild new rules it created, and finally, this golden age of creativity that came out of it all. All right, let's jump in. Picture this. It's the late 1950s. The electronics industry has these huge dreams, but it's about to slam headfirst into a very real, very physical wall. And the biggest threat, the thing that was holding everything back, it wasn't a lack of brainpower or a shortage of big ideas. Nope. It was something way simpler, and honestly, way more frustrating. There were just too many parts. Too many tiny individual components that all had to be soldered together by hand. This right here, this was the tyranny of numbers. See, as engineers tried to build more powerful computers, the number of parts just exploded into the thousands. And with every single one of those soldered joints being a potential point of failure, well, the odds of something going wrong got closer and closer to 100%. The bigger you built it, the more certain you were that it was gonna break.
So the answer couldn't just be, get better at soldering. It had to be a total rethink of the whole problem. Someone had to figure out how to build a complicated circuit without all those individual connections. What if you could just make it all from one single piece of stuff? And that someone was a guy named Jack Kilby. He was a new engineer at Texas Instruments, and he decided to stay at work while the whole company was on summer shutdown in 1958. He used that quiet time to sketch out his idea for a solid circuit. And get this, just a few weeks later, on September 12th, he showed it off. He proved for the very first time that a working circuit could exist on a single piece of material. Now, here's where you can see both the genius and the problem with Kilby's invention. He built a working circuit on this tiny sliver of germanium, which is amazing. All the parts were carved from the same block. But look closely. To connect everything, he still had to use these ridiculously tiny, delicate gold wires, the flying wires, and solder them by hand. It was an incredible proof of concept for sure, but there was no way you could mass produce something that fragile.
So Kilby had proven the concept was possible. Awesome. But to turn that brilliant idea into a technology that could actually change the world, someone had to solve the problem of those fiddly flying wires.
And way out in California, another amazing engineer, Robert Noyce, was tackling the exact same problem. But his focus was a little different. He wasn't just thinking, can we make this work? He was obsessed with, how can we make 1 million of these reliably and cheaply?
And Noyce's approach, this was the game changer. First he used silicon, not germanium, and here's the crucial bit. Instead of those fragile flying wires, he used a new process to basically print flat aluminum connections right onto the chip, and then sealed them under a protective layer. It was all one solid, self-contained, monolithic thing. That was the key to mass production.
And this really gets to the heart of it. While Kilby absolutely deserves credit for the foundational idea, it was Noyce's elegant manufacturable design that created the blueprint. Seriously, every single computer chip made today, including the one in whatever device you're watching this on right now, is a direct descendant of Noyce's planar chip. Okay, so problem solved, crisis averted, right? Not so fast, because this is where the story gets really interesting. Solving the tyranny of numbers created a brand new, totally unexpected problem, one that flipped the entire world of circuit design on its head.
The entire economic model for electronics just inverted. I mean, completely. In the old world, with all the separate parts, transistors were the expensive, precious things you used as little as possible. Resistors and capacitors, they were dirt cheap. But on a silicon chip, the exact opposite was true.
And here's why. It all came down to one thing: real estate. On a chip, cost wasn't about money per part anymore. It was about the physical space a part took up. A transistor was microscopic, but a resistor needed this long strip of material taking up a ton of space. And a capacitor? Oh man, a capacitor was a monster. A single one could literally take up the entire chip. So you have this new, totally backwards reality. It was a massive constraint, right? It basically forced engineers to throw out decades of established design rules and just start over. They had to come up with completely new ways of thinking.
I mean, think about it. All their standard tools, their go-to techniques that relied on having plenty of cheap resistors and capacitors, all of that was suddenly off the table. Completely impractical. They had to go right back to the drawing board.
So what do? They came up with a new philosophy. The new playbook was simple. Since transistors were now practically free and took up almost no space, you should use them for everything. They invented these wild new circuit designs that used bunches of transistors to do the jobs that a single, now expensive resistor or capacitor used to handle.
And here's the incredible part. This massive limitation, this thing that should have slowed them down, it did the exact opposite. It ignited a firestorm of innovation. It forced a level of creativity that the field had just never seen before, leading to what people still call the golden age of analog design. The solution to one problem created a new constraint, and that constraint unleashed a wave of absolute genius.
Today, we're going to talk about a guy who was, well, a true rebel. He was a brilliant engineer who took on a problem that everyone else thought was impossible. And by solving it, he basically launched the entire multi-billion-dollar analog chip industry all by himself. It's a fantastic story about genius, pure stubbornness, and seeing a path forward where everyone else just saw a dead end. So let's start with the central puzzle that had engineers in the early 1960s just completely stumped. You see, for decades, designing circuits meant you could rely on your parts to be predictable, to be stable. But the moment you tried to shrink everything down onto a tiny silicon chip, all that stability just went out the window. So the big question was, how in the world do you build something perfect using parts that are fundamentally imperfect? And this really gets us to the first major roadblock, the very nature of this impossible chip. Okay, so what you're seeing here are two completely different worlds colliding. On the left, you've got the old way of doing things. Big, bulky circuit boards with components you could count on. You knew what they were going to do. But on the right, that's the future. A single, tiny piece of silicon. The problem? The little parts on that chip were just all over the place, totally unreliable. You couldn't just take the old designs, shrink them down, and hope for the best. It just didn't work.
And I mean, this was a huge problem. Take a resistor, one of the most basic building blocks in electronics. Its actual value on a chip could be off by as much as 20%, plus or minus. Imagine trying to build a precision watch when the seconds on your clock could randomly be 20% longer or shorter. It was a complete nightmare for designers. So to solve a problem this big, you couldn't just make slightly better parts. No, you needed a completely new way of thinking about the problem itself. And that, of course, required a new kind of thinker. And that's where Bob Widlar comes in. Fairchild hired him in 1963, and this guy was an absolute genius. He just had this gut-level understanding of transistor physics that almost no one else on the planet had. He would, and I'm not exaggerating, become a legend.
But here's the thing about Widlar. He was also famous for, let's say, not loving corporate rules. He was known for his hard drinking, his wild pranks. He was basically the perfect symbol of that brilliant, chaotic culture that would later define Silicon Valley. He just wasn't the kind of guy who heard the word impossible and decided to pack it in.
And this right here was Widlar's flash of genius. He realized that, okay, you can't trust the exact value of any one resistor. But, and this is the key, two resistors built right next to each other on the chip would be almost perfectly matched. They might both be 18% off, but they'd be off together in the exact same way. So he decided to build his designs around these super reliable ratios and just ignore the flawed individual values altogether. Brilliant. So, armed with this radical new philosophy, Widlar set out to build something that shouldn't exist. A whole amplifier on one tiny piece of silicon. And in 1964, Fairchild released his creation to the world, the MU-A702. I mean, this was truly historic. It was the very first time an entire operational amplifier, or op-amp, had ever been crammed onto a single monolithic chip. But it was, let's say, far from perfect. It was kind of what you'd call a noble failure. On the one hand, it proved the whole concept could actually work, and it literally created a market for these things out of thin air. On the other hand, it was an absolute beast to use. It needed weird, non-standard power supplies, it was super hard to stabilize, and a lot of the time it would just start oscillating like crazy instead of amplifying anything. Now, Widlar wasn't satisfied at all. I mean, proving something was possible wasn't enough for him. He wanted to make something that was actually useful, something people could build with. So he went right back to the drawing board to create his masterpiece. And just a year later, in 1965, he did it. He unveiled the UA709. And this was the one. It was a massive leap forward. It became the very first analog chip to sell in the millions, and it's the chip that really truly launched the analog industry that we know today. The 709 was just packed with these clever little innovations, but one of the most brilliant was something called the Widlar current source. See, the problem was this. To get a tiny, stable current on a chip, the math said you needed a massive 1 mega-ohm resistor. A part so physically huge, it would have taken up more space than the rest of the circuit combined. So Widlar's trick was to use two tiny transistors to mirror and shrink a current, getting the exact same result but using a tiny resistor. It was just an incredible hack that saved a ton of precious space on the chip. His second secret weapon was, if you can believe it, even more backwards. You see, the manufacturing process was really good at making one kind of transistor, but also created this other kind, the lateral PNP, as this unavoidable low-quality byproduct. I mean, these things had awful performance. Most designers just saw them as useless junk to be ignored. But Widlar saw potential. The story goes that Widlar literally locked himself away for 170 hours, just obsessively poking and prodding at these lousy parts until he figured out how to make them do a useful job. It just proved his core philosophy. A really clever designer could do more with bad components than a mediocre designer could ever do with perfect one. So the MU-A709 was a runaway success. It launched an entire industry. But even this masterpiece wasn't quite perfect. And funny enough, its flaws are what created the next big wave of innovation. For one thing, the chip was really fragile.
If you made one simple mistake, like accidentally shorting the output pin to ground, poof, the whole thing would instantly overheat and destroy itself. And it still needed a couple of external parts to keep it stable, which was kind of a hassle for designers. Really, these flaws just became the next set of challenges for the next generation of engineers to solve.
Maybe the most legendary resignation letter in the history of tech. In 1965, a brilliant but very frustrated engineer, Bob Widlar, quit his job at Fairchild Semiconductor. His official notice? This. Just a single, defiant line drawn across a piece of paper. This wasn't a resignation, it was a declaration of war. You see, by the mid-60s, Fairchild was a titan in the industry, but its culture was getting, well, corporate. It was bureaucratic. Management was far away, and for a guy like Bob Widlar, who was as abrasive as he was brilliant, it was totally stifling. He knew what he was worth. He demanded a huge raise, and when the company said no, he walked. Just like that. But Widlar didn't just leave. He jumped ship to a much smaller, struggling company called National Semiconductor. And this move, it created this fascinating clash of cultures. He helped turn National into the complete opposite of Fairchild. It was aggressive, a Wild West kind of place. The perfect environment for a genius with a serious grudge. So, with his new home secured, Widlar set his sights right back on his old one. It was time for a little payback. Designed in silicon. In 1967, Widlar unleashes his masterpiece of revenge, the LM101 operational amplifier. Now, this wasn't just some new chip. This was a direct shot at Fairchild's most popular op-amp, the UA709. It was engineered from the ground up to be better in every single way imaginable. And the LM101 really was a marvel. It used these innovative super beta transistors, which gave it way better performance. It simplified all the complicated external circuits that engineers hated dealing with, and it had built-in protection that made it pretty much indestructible. It was a superior product, and of course, it was designed by the one guy who knew all of Fairchild's weaknesses from the inside. National had landed a serious blow, but this war, it was far from over. Back at Fairchild, a new engineer was about to change the game forever. So, a young engineer at Fairchild named Dave Fulligar gets the job of responding to Widlar's attack. He studies the LM101, and he realizes that for all its genius, it still had one tiny inconvenience. Engineers still had to add this one little external component, a tiny 30 picofarad capacitor, just to make it stable. And this right here was his aha moment. Fulligar's idea was so simple, it was brilliant. He thought, what if we could just build that last little part, that capacitor, directly onto the silicon chip itself? Now that was a bold move because space on a chip was precious real estate, but if he could pull it off, it would be absolutely revolutionary. And what's really crucial here is the sheer speed of all this. Just think about it. Widlar resigns in 65. He strikes back with the incredible LM101 in 67, and then just 1 year later, in 1968, Fairchild fires back with its answer, the UA741. We're watching an entire industry get completely reshaped in just 3 short years. This evolution just shows you what an incredible leap it was. The old UA709, it needed a bunch of complex external parts. Widlar's LM101 simplified that down to just one. But Fulligar's UA741, it was pure plug and play. An engineer could just connect power, and it worked. Its killer feature wasn't just performance, it was radical simplicity. So the UA741 didn't just win the battle. It established a whole new design philosophy, one focused on making things incredibly easy for the user. It became something much, much bigger, the industry's very first jelly bean component. So what on earth is a jelly bean component? Well, it's a term for a part that's so cheap, so reliable, and so easy to use that it just becomes ubiquitous. It's everywhere. It's the default choice, the go-to part you find in countless designs, like grabbing a handful of jelly beans. And the UA741 was the first analog chip ever to earn that title. And its legacy is just staggering. The design was so good, so robust, and so incredibly useful that the UA741 is still being manufactured and sold today, over half a century later. That is absolutely wild. It is, without a doubt, the most popular analog integrated circuit in history. But here's the big twist in our story. While these companies were basically at war from 9 to 5, their top soldiers were often sharing secrets at night. And their neutral territory was a bar.
The Wagon Wheel Bar in Mountain View was the unofficial social club for Silicon Valley's brightest minds. You'd have rivals from Fairchild, National, and all the other big players gathering here. And after a few beers, those corporate allegiances, they started to get a little blurry.
See, inside this bar, a kind of unofficial collaboration was happening. Information just flowed. Engineers would brag, they'd complain, and they'd sketch out brand new circuit ideas on cocktail napkins. This cross-pollination of ideas, fueled by a potent mix of beer and ego, became a massive accelerator for innovation. The very war they were fighting during the day was being shaped right here at night.
Catastrophic. I mean, just think about that word. That's what engineers back in the 1970s were saying about a tiny, almost invisible error buried deep inside their most important components. For things like medical instruments or critical industrial sensors, this wasn't just some small glitch, no, it was a total deal breaker.
You see, everything we think of as digital today, our phones, our computers, all of it had to be built on an analog foundation. And that foundation, it had a crack in it. To move forward, they had to reach a level of perfection that honestly seemed almost impossible at the time. So this isn't a story about one single invention. Nope. Instead, it's a tale of two parallel paths, two completely different philosophies that would ultimately come together to shape our modern world.
All right, so what was this catastrophic error that had everybody so worried? Well, it all comes down to a concept called offset voltage.
Let me give you an analogy. Imagine you have a bathroom scale, but it reads 1 kilogram before you even step on it. Every single measurement you take from then on is going to be wrong by exactly that much. Well, offset voltage is basically the electronic version of that. It's this tiny built-in error in an amplifier that corrupts every single signal that passes through it.
So on the left, you've got the workhorse of the era, the 741 operational amplifier. And look, it was good enough for a lot of things, but it had a massive offset voltage. On the right, that's the goal, a precision amplifier for scientific and medical instruments, where even the tiniest error could mean the difference between a correct diagnosis and a disaster. The gap between them was huge. So our first genius tackled this problem head-on with a solution that was direct, powerful, you could almost call it brute force. Let's meet George Ardie.
Okay, so picture this. It's 1975. George Ardie is working at a company called Precision Monolithics, and their entire mission, their whole reason for being, was to create chips with the same accuracy as super high-end lab equipment. And his number one target? That pesky offset voltage in chips like the 741. He was about to completely change the game.
And this chart, wow. This just shows you how wildly successful he was. I mean, look at this. The standard 741 op-amp had an error of up to 5,000 microvolts. Ardie's new chip, the OP7, slashed that error all the way down to just 10 microvolts. That's not just an improvement, that is a revolutionary leap. We're talking hundreds of times better. So how on earth did he do it? You know, the old methods involved using lasers to physically burn away parts of the chip, a process that was really expensive and not very reliable. Ardie's solution was so much more elegant. He called it Zener zapping. The whole process was just ingenious. Ardie placed these special little components, called Zener diodes, right next to the resistors that controlled the amplifier's balance. Then, during factory testing, they'd send a high current pulse, a zap, right through it. This zap would cause the diode to break down, allowing the aluminum contact to literally melt and create a permanent short circuit. So, by selectively zapping these diodes, engineers could digitally trim the resistors and balance the amplifier to near-perfect symmetry.
Okay, so let's shift gears and meet our second genius. Because while Ardie was basically forcing silicon into submission, Barry Gilbert was taking a totally different approach. He was listening to it. You know, he was trying to understand its fundamental physics. So while Ardie's whole world was about controlling voltage, Barry Gilbert, a British engineer, was fascinated by something else entirely: the beautiful, hidden mathematics of electrical current flowing through transistors. He formalized this incredible idea called the translinear principle. And the core of it is amazing. Instead of fighting the physics of a transistor, you use it. He realized that the relationship between voltage and current in a transistor follows this natural mathematical curve. So by arranging transistors in special loops, you could get them to do math, multiply, divide, even find square roots of analog signals, performing complex calculations instantly without needing a slow, power-hungry digital computer. So we have these two incredible breakthroughs, one taming voltage, the other unlocking current. how did all this pure theory translate into the real world? Well, the truth is, it's in almost everything. Gilbert's most famous invention is the Gilbert cell. It's basically his translinear principle in action, a circuit that can multiply two analog signals. This became the heart of the AD534 chip back in 1976, and suddenly you could calculate things like real-time power, voltage times current, instantly. No more slow, expensive digital computers. This was a revolution for measurement and communication.
And here's why this all matters to you, right now. George Erde's Precision OP07 became the absolute gold standard for medical and industrial sensors, where accuracy is everything. And Barry Gilbert's cell? Oh, that's the core component in basically every radio and cell phone on the planet, used for mixing frequencies. His translinear circuits are also critical for things like the digital multimeters you might have in your garage.
So let's bring these two incredible stories together and take a look at the legacy they created. This table just sums it all up perfectly. You have Erde, who mastered voltage, forcing precision onto silicon with his Zener zapping. And then you have Gilbert, who mastered current, discovering the math that was already hidden in the physics of transistors. One gave us flawless measurement, the other gave us high-speed analog computation. Two completely different paths to perfection.
I really love this way of thinking about it. Erde was a master craftsman taming the chaotic imperfections of raw silicon. Gilbert, on the other hand, was a composer arranging transistors to play a perfect mathematical symphony.
And here's the ultimate takeaway. We live in what we call a digital world, but every single bit and byte originates from and has to interact with the real analog world. That interface is only possible because of the incredible precision that was forged by these analog pioneers. So, you gotta picture this. Back in the 1970s, technology was basically split into these two totally opposite camps. On one side, you've got this brand new world of digital. Everything's clean, logical, super orderly. It's all just simple ones and zeros. But then, on the other side, you've got, well, the real world, the analog world. And it's messy, it's chaotic, it's continuous, it's made of stuff like sound waves and heat and pressure. And here's the big problem. These two worlds, they couldn't speak the same language at all. And that created a massive problem, a huge divide. See, we started getting these incredible new microprocessors, like the Intel 4004. So we had these powerful digital brains, right? But they were basically deaf and blind. They had no way to sense the real analog world that they were supposed to be interacting with. So where did the solution come from? Well, it didn't come from some sterile, buttoned-down corporate lab. No way. It came from this whole new breed of engineer out in Silicon Valley. These guys were, well, they were rebellious. They were individualists. A culture of brilliant minds who trusted what they could build with their own two hands, way more than they trusted what some computer could tell them.
And this whole attitude, it was perfectly captured by legends like Bob Pease. Back then, early computer simulations, there was this one program called SPICE. They were looked at with deep suspicion. Pease had this famous saying, "Physics works, SPICE lies." What he meant was, they believed these neat little simulations were hiding the messy truth. These real-world electronic gremlins. You know, tiny, unpredictable things like stray capacitance or heat gradients that could completely wreck a circuit. So what they do, instead of simulating, they just built stuff. They were all about physical prototyping. And their workbenches, they were famously chaotic. I mean, just piled high with these circuits, built in 3 dimensions, components literally soldered to each other in midair. They called it deadbud style. And it wasn't just about being messy. It was a technique. It was how they got a visceral and intuitive feel for how the electronics would actually behave out in the real world. And this whole hands-on approach, it was part of a much bigger ethos. These engineers, they really saw themselves as cowboys, not as, corporate drones. They totally rejected that slow, designed by committee thing that was happening at the big East Coast giants like IBM or Bell Labs. Nah. They believed that a single, brilliant, risk-taking individual, they could achieve way more, way faster. And their anti-corporate spirit, it was absolutely legendary. There's this great story. So, National Semiconductor decides to cut the groundskeeping budget. What does engineer Bob Widlar do? He brings a sheep, in his Mercedes convertible no less, tethers it to the front lawn and then calls a reporter to come document the new maintenance crew. I mean, come on, it was just this perfect, defiant symbol of that whole rebellious culture. Okay, so you've got these cowboys, and they're in this incredibly high-stakes race. Their mission, their whole goal, was to build the ultimate bridge.
a bridge between the analog and the digital worlds. This bridge had a name, a data converter. It was a device that could finally translate the language of the real world into the ones and zeros that a computer could actually understand. Now, the holy grail here was to make this bridge monolithic. What does that even mean? Well, it means shrinking what used to be this clunky, really expensive module made of a ton of different parts and squeezing it all down onto one single, elegant, tiny piece of silicon. The first team to pull that off, they were going to change electronics forever. But of course, there was a huge obstacle standing in their way. Think about it. To measure anything, you need a ruler, right? A perfectly stable one. Well, in electronics, that ruler is something called a voltage reference. And the problem was, all the options they had at the time, like this thing called a Zener diode, were totally unreliable. They were noisy, and their measurements would just drift all over the place as soon as the temperature changed. Their ruler was basically wobbly. You can't measure anything accurately with a wobbly ruler. And then came the breakthrough, the invention of that perfect, stable ruler. It happened in 1974. An engineer over at a company called Analog Devices, a guy named Paul Brokaw, he had this moment of just pure genius. So what Brokaw invented was called the band gap reference, and it was a total game changer. Remember how the old Zener diodes were noisy and would drift with heat? Well, his new circuit was unbelievably stable. It worked on low voltage, and this is the key part, it was almost completely immune to changes in temperature. Just like that, he had solved the wobbly ruler problem. So you're probably asking, how in the world did he do it? The solution was just incredibly elegant. Brokaw's circuit takes two transistors, and here's the genius part. They have opposite reactions to heat. So as the temperature goes up, the voltage on one of them drifts a little bit higher. At the same time, the voltage on the other one drifts a little bit lower. By combining them in exactly the right ratio, the two opposing drifts just canceled each other out perfectly. And the results of this beautiful little balancing act? A near-perfect, temperature-immune 1.25 volt ruler. This was it. This was the stable reference they had all been dreaming of. And the best part? It could be built right onto the silicon chip itself. So now, with that perfect ruler in hand, the path was totally clear. In 1978, Brokaw and his team released something called the 8571. And this was the big one, the world's first complete, monolithic, analog-to-digital converter. For the very first time, that hard line between the analog and digital worlds, it started to blur, right there on the silicon itself. Now, this breakthrough wasn't just some technical achievement for the history books. No, it created a legacy. A legacy that, whether you realize it or not, is living inside every single smart device you use, right now, today. You can kind of see the whole story unfold here. The 1970s was just this incredible whirlwind decade. You've got the digital shift starting, you've got the wobbly ruler problem getting solved, the first monolithic bridge it's built, and that whole Wild West startup era, it starts to mature. It all happens so fast. And here's the real kicker. Here's why this stuff matters to you. The fundamental designs that were pioneered by these analog cowboys, they're literally the DNA of modern electronics. The op-amp design in your headphones, the little circuit that mixes signals in your 5G phone, and yep, that brilliant bandgap reference that's stabilizing the voltage in your laptop right now, every single one of them traces its roots straight back to this golden age.
Let's go back to the world before 1980. This was a totally different time, a golden age for a technology called analog. And it was ruled by a completely different kind of electronic component. And this guy right here was the king, the bipolar junction transistor, or BJT for short. Back in the 70s, if you were an engineer dealing with real-world stuff like audio for your stereo or radio waves for your TV, the BJT was your absolute go-to. It was literally built from the ground up to handle that smooth, continuous flow of analog information.
So what made the BJT so special for analog? Well, think of it like this. It was an incredible amplifier. It could take a tiny, weak signal and make it huge without adding a bunch of static or noise. Plus, and this is key, every BJT you made was super predictable. That made it easy to build really precise, high-fidelity circuits. For an analog engineer, this thing was a perfect tool.
But then, everything started to change. There was this huge wave building on the horizon, a wave powered by the rise of personal computers. It was a digital tsunami, and it was about to crash over the entire industry.
And here's the big shift. This new digital world cared about completely different things. It wasn't about perfect sound quality anymore, it was all about density, cramming millions of tiny switches onto a chip, and doing it using as little power as possible. And those were two things that bipolar technology was, well, just awful at.
This basically split the electronics world in two. On one side, you had bipolar, the analog champ. High performance, yeah, but it was a power hog. On the other side, this new kid on the block called CMOS. And CMOS was a digital dream come true. You could pack millions of them onto a chip. And here's the magic trick. It barely used any power unless it was actively switching. That efficiency made CMOS the engine of the entire computer revolution. And this is what led to what everyone in the industry started calling the great analog dilemma. All of a sudden, these two worlds, analog and digital, that had lived completely separate lives with their own technologies, were being forced to move in together. This quote really gets to the heart of it. This wasn't just a simple choice. It was a problem baked into the laws of physics and the demands of the market. You see, the very properties that made bipolar a beautiful analog tool made it a terrible digital one. And the things that made CMOS a perfect digital switch made it a noisy, unreliable mess for analog signals. But economics demanded they figure out how to live together on one chip.
And the reason was pretty simple. Everybody wanted a system on chip. The holy grail was to shrink an entire device, the processor, the radio, the audio circuits, everything, onto one single piece of silicon. That would make our gadgets way cheaper, way smaller, and way more powerful. But it created a huge problem. It meant the delicate, sensitive analog circuits had to be built using the digital technology CMOS.
For analog designers, this was a total nightmare. I mean, trying to build a sensitive audio circuit with CMOS was like trying to perform brain surgery with a sledgehammer. It was noisy, the transistors were weak amplifiers, the performance would drift all over the place as the chip heated up, and they just didn't have the muscle to drive strong, clean analog signals. It was a terrible
So what do you do? What do you do when the very physics of your building blocks are fighting you every step of the way? Well, you don't fight harder, you fight smarter. The next part of this story isn't about some new wonder material. It's about pure, raw engineering cleverness. This was the big aha moment. The engineers realized they couldn't just force CMOS to be something it wasn't. They couldn't change the physics. So instead, they decided to outthink the problem. They had to invent completely new circuit designs, new architectures, that would cleverly work around all the weaknesses of the transistors they were forced to use.
And this is where the real genius shines through. To solve the weak amplification problem, they came up with these incredibly clever circuit layouts, like the folded Cascade amplifier, that basically stack transistors to multiply their power. To get precision out of imprecise parts, they developed a brilliant trick using tiny switches and capacitors, creating filters that were actually made more accurate by the digital clock signals, not less. And eventually, this kind of thinking led them to figure out how to build entire radio systems on a CMOS chip, something everyone thought was absolutely impossible.
So what was the result of all that incredible ingenuity? Well, it's the world you and I live in today. It's a world where our entire digital life, all our communication, all our computing can live on a single, tiny fleck of silicon. And this was the ultimate prize, the system on chip, or the SoC. Because those engineers solved the analog dilemma, these modern marvels became possible. A single chip that has the analog parts that listen to the world and the powerful digital brain that thinks about it, all living together side by side.
And make no mistake, this isn't some obscure niche technology. This mixed signal integration is the bedrock of our modern world. It is in the phone in your pocket, it's in the computer you're watching this on, it's in your car, it's in your watch. The solution to that old analog dilemma is literally all around us every single day.
A battle between two very, very different types of transistors. So, in one corner, you've got the bipolar transistor. This was the undisputed king of the analog world.
And then, in the other corner, you have the MOS transistor. Now, this thing was fantastic for creating tiny digital switches, the building blocks of computers. But as an amplifier, oof, it was kind of terrible.
But here's the thing. The MOS transistor was the little engine that could, driving Moore's law. You know, that relentless, unstoppable demand for smaller, faster, and denser digital chips that has pretty much defined the last half-century of technology. And this is where things get really, really interesting. A paradox started to emerge. The very thing that made MOS transistors great for digital, shrinking them down, made them even worse for analog. As they got smaller, their ability to maintain a stable output just plummeted. And that caused their internal amplification, their gain, to completely collapse. So you see the crisis brewing, right? Designers were in a real bind.
They desperately needed the precision of analog circuits to let our digital devices talk to the real world. But their main building blocks were getting worse with every single new generation. The old ways of designing things, they just weren't going to cut it anymore.
Traditionally, the way you'd get high gain was to literally stack transistors on top of each other. It's a configuration called a telescopic cascade. This setup was great for boosting gain, but it had one huge drawback. It needed a lot of voltage headroom to work. You can think of it like needing a really high ceiling to be able to stand up straight.
And that headroom? Well, it was disappearing, and fast. As Moore's law kept pushing transistors to get smaller, the voltages they ran on had to drop to keep them from literally burning out. We went from 12 volts, down to 5, then down to 3.3, and it just kept getting lower. That tall stack of transistors just couldn't fit anymore. The ceiling was getting lower and lower.
So what was the answer? It wasn't some new magic material or a revolutionary new transistor. The solution was something much more elegant. It was a simple change in geometry. Instead of stacking up, designers figured out how to fold the circuit. And this new idea was perfectly captured in the folded Cascade amplifier. Instead of sending the signal straight up through that tall stack, it cleverly folded the current path, almost like an elbow, redirecting it into a different part of the circuit. It's just like taking a tall ladder, folding it in half, and suddenly being able to fit it into a room with a low ceiling. This one ingenious geometric trick allowed designers to get around the weaknesses of the individual parts by just arranging them in a much smarter way.
And just like that, this design became the essential tool. It was the new workhorse for every analog designer out there. It proved that how you laid out the circuit, the geometry, could be more important than the physical flaws of the components themselves. Now, a brilliant idea like this doesn't just pop out of thin air. It was actually the result of a complete revolution in engineering thinking led by some true pioneers in academia, who basically had to rewrite the engineering Bible for a new era. This whole revolution really kicked off in the mid-70s, when a graduate student, Ioannis Savidis, did what a lot of people thought was completely impossible. He built the very first operational amplifier, an op-amp, using MOS technology. After that breakthrough, researchers like Paul Gray and Robert Meyer at UC Berkeley started to formalize this new science, turning it from a bunch of clever tricks into a rigorous, predictable engineering discipline. What they did was teach an entire generation of engineers a whole new way of thinking. They taught them to stop trying to find perfect, high-quality components and instead start designing smarter systems. The focus shifted from the quality of the one transistor to the cleverness of the whole circuit.
And that textbook from Gray and Meyer, it became the Bible for a whole generation of engineers. It gave them the mathematical foundation, the tools, and frankly, the confidence they needed to build these super precise analog circuits right alongside millions of noisy digital switches on the very same chip.
And the legacy of this whole revolution is what we now call the mixed signal chip. You know, you might look at a chart like this and think that analog part looks kind of small, but don't let that fool you. That little slice is the absolutely critical interface to the real world. It's the eyes and ears of the digital brain, and it's at the heart of pretty much every single device we use. Seriously, this legacy is all around you. It's in the transceiver in your smartphone connecting to the cell tower. It's the Wi-Fi and Bluetooth radios in all your gadgets. It's in the sensor in your camera capturing a photo. All of these technologies depend on those foundational analog design techniques, like the folded Cascade, that were born out of necessity all those decades ago.
All right, so in the world of analog chips, what engineers needed were filters that were basically perfect. You know, precise, stable, and tiny. But what they could actually build on a silicon chip? It was the exact opposite. I mean, it was a total nightmare. Wildly imprecise, unstable, and just absolutely enormous.
And just how imprecise are we talking here? Well, the core components they were using, these things called resistors, could be off by a shocking 20% right out of the factory. Think about that. It's like trying to build a house with a ruler where every inch might actually be off by that much. It was completely unworkable. Yeah, there's a reason this was called an insidious problem. It wasn't just that these resistors were imprecise. They were monstrously large. To get the kind of resistance you needed for a telephone filter, a single one of these components could take up more precious silicon real estate than the entire processor it was supposed to be helping. This was a huge barrier to making things smaller. And look, this wasn't just some brain teaser for engineers to solve in a lab. This one little imperfection threatened to stop one of the biggest technological projects of the 20th century dead in its tracks, the dream of a global digital telephone network. Okay, so here's why it was such a massive deal. Every single phone line in the world needed a super precise filter to make the switch from analog voice to digital data. The standard said you had to cut off frequencies above exactly 3.4 kilohertz, but with a 20% error, that cutoff could be way down at 2.5 or all the way up at 4.5 kilohertz, completely scrambling the signal and making the line useless. The whole plan was stuck.
So how in the world did they break this deadlock? Well, the solution didn't come from some new exotic material. It came from an elegant, almost forgotten idea, an insight that had been sitting on a dusty shelf, so to speak, for over 100 years. The story starts way back in 1873, and it starts with an observation from the legendary physicist James Clerk Maxwell. Yep, that Maxwell, the electromagnetism guy. He noticed something really curious about capacitors, but the idea just kind of laid dormant for a century, until the late 1970s, when a new generation of chip engineers stumbled across it and saw its incredible potential. So what was this brilliant idea they resurrected? It's called a switched capacitor. And the concept is actually beautiful in its simplicity. Instead of a bulky, messy physical resistor, you use a tiny capacitor and two microscopic switches. By flipping these switches back and forth incredibly fast, guided by a super precise clock, you can shuttle these tiny exact packets of electrical charge from one spot to another. And that action perfectly imitates the smooth flow of current through a resistor. Now this is where the real genius kicks in. It totally reframes the problem. You just charge a capacitor, flip a switch, discharge it, and then do it again millions of times every second. All of a sudden, your resistance isn't based on some flawed physical material anymore. It's based entirely on something you can control with near-perfect accuracy, time. Okay, so let's put these two head to head. You'll see just what a game changer this was. The old filters, they depended on messy material properties, which is where you get that massive 20% variance. But the new switched capacitor filters, they only depended on two things engineers could control with incredible precision: the ratio of the sizes of two capacitors and the speed of a digital clock. And that leap in precision, wow, that was everything. Just look at this chart. We go from a 20% variance with the old resistors all the way down to less than 0.1% with switched capacitors. That is an incredible 200-fold improvement in accuracy. It was exactly the breakthrough everyone had been waiting for, and this quote just nails it. They traded an unsolvable material science problem for a problem of geometry and time. And guess what? Those were two things that the new CMOS chip-making process was amazing at: creating really precise geometric shapes for the capacitors and keeping perfect time with a crystal clock. So you can bet this breakthrough technology did not stay in the lab for long. It almost immediately found its killer app, the very chip that was going to connect the world's voices. The hero of our story is this chip right here, the Intel 2912. Now, it's not famous like the Pentium or anything. You've probably never heard of it. But this little piece of silicon was a true watershed moment in telecommunications. You could argue it was just as important to our connected world. The Intel 2912 was the proof. It used switched capacitors to put all of those super accurate filters for a phone line right onto a single chip. This got rid of expensive manual adjustments, it easily blew past the world's strictest telecom standards, and, maybe most importantly, it absolutely crashed the cost of going digital. Now, the secret ingredient that made this possible was a parallel innovation in manufacturing. Process engineers perfected something called the double poly process. So, in simple terms, it let them add a second, ultra-pure layer of a material called polysilicon, and this created nearly perfect, super stable capacitors right on the chip. It was the perfect hardware for this brilliant new design. But the legacy of the switched capacitor, it's so much bigger than just this one chip, or even the whole telephone network. It fundamentally changed how engineers thought about solving problems with silicon. So, at the end of the day, what we're looking at is a total triumph of elegant design over brute force material science. It proved you could build precision analog circuits on standard digital chips, and that fueled a global communications boom. And it really just demonstrated a timeless principle. Sometimes the best answer isn't a new material, but a brilliant new way of thinking. Welcome to The Explainer.
Today, we're going to talk about a brilliant little engineering trick, a clever workaround that took high-fidelity digital sound from these super expensive specialist pieces of gear and put it, well, everywhere. It's a great story about how to solve a problem by just thinking about it completely differently.
Okay, so let's just start with the puzzle at the heart of all this. How on earth did a really, really crude 1-bit chip give us pristine 16-bit CD quality sound? I mean, it just sounds impossible, right? A single bit? Well, the solution to this puzzle completely changed consumer electronics, and it all boils down to one simple, powerful idea.
And this is it. This is the core philosophy. Use thousands of cheap digital transistors to correct the deficiencies of a few analog ones. It's this beautiful story of letting the digital world, with its incredible power and scalability, clean up the messy, imprecise reality of the analog world.
Now, to really appreciate just how revolutionary that idea was, we have to go back to the early 90s, when engineers were slamming face first into a massive wall. It was a problem of precision. Just look at this number for a second, 0.00015%. That is the absolutely mind-boggling level of precision that you needed from your analog components to create a standard 16-bit digital audio signal. To put that in perspective, that's like trying to match components to within 1 part in 65,536. It's like trying to find one specific person in a massive sold-out stadium. You can imagine that trying to do this with old-school analog methods wasn't just hard, it was ridiculously expensive and fragile. And this slide really shows you the problem. The old way of building these converters, the way companies like Burr Brown did it, relied on brute force. You had to have these perfectly matched analog parts. They literally had to use lasers to trim them during manufacturing. They were super sensitive to temperature. And worst of all, this approach just didn't scale. It couldn't follow Moore's law and get cheaper and smaller and better every year. It was a total dead end for making stuff for the mass market. So the industry was stuck. They desperately needed a new way of doing things. And instead of trying to fight for this impossible analog perfection, they came up with a wild idea to just outsmart the problem using digital cleverness. So the first part of the trick was a technique called oversampling. Now, think of it like this. Instead of taking just enough photos of a fast-moving car to see what it's doing, you take like 100 times more photos. By sampling the audio at an insanely high rate, we're talking 64, 128, even 256 times higher than necessary, they got a super detailed picture of the sound. And this had a really cool side effect. It spread out all the unavoidable digital errors over a much wider space, which made them a whole lot easier to deal with. But oversampling was just setting the stage. The real genius, the absolute heart of this whole trick, was what they did with all that digital noise. This is the magic trick, right here in 4 steps. So first, you oversample, like we just talked about. Then you quantize that signal using a ridiculously simple 1-bit converter. And then, and this is the key part, a clever little feedback loop acts like a bouncer at a club. It literally takes all the unwanted digital errors, all that quantization noise, and shoves it way, way up into the super high frequencies, so high that no human could ever hear them. And once all that noise is pushed way out of the way, a simple digital filter just comes in and chops it all off. What you're left with is a clean, beautiful high-resolution signal. And here's the most incredible part of all. All of that complicated heavy lifting, the stuff that used to require a complex, expensive, fragile analog monster, it was now being done by a simple, cheap 1-bit comparator. The need for brute force precision had been moved out of the hardware and into a really, really clever algorithm. So why 1-bit? Why was that so important? Well, it's because a 1-bit system is, by its very nature, perfect. It only has 2 points, right? 0 or 1, on or off. And any 2 points define a perfect straight line. This means it's inherently linear. It completely sidestepped that whole analog component matching problem that plagued the old designs. There was literally nothing you needed to match. It was perfect by default. This comparison chart just lays out the entire philosophical shift so perfectly. The complexity moved from the expensive, delicate analog side to the cheap, powerful, and constantly improving digital side. This new Delta Sigma way scales perfectly with Moore's law, which meant high-quality audio could get cheaper and better, year after year after year. And this whole thing wasn't just some academic exercise in a lab. No, this breakthrough completely changed the game for consumer electronics. It directly led to the sounds of the 1990s and really everything that came after.
You had these pioneers, right? Companies like Crystal Semiconductor over in the US and Philips in Europe. They jumped on this theory and quickly turned it into actual chips that you could buy, chips that powered a whole new generation of devices. Crystal especially just took over the market for PC sound cards.
And the impact? Oh, it was enormous. This tech was the engine behind the whole 90s multimedia boom. All of a sudden, your PC wasn't just making little beeps and boops anymore. It could play back full CD-quality audio. High-fidelity sound wasn't just for audiophiles with expensive hi-fi systems. It was in your portable CD player. And really, it laid the entire foundation for the MP3 players that were just around the corner.
But here's the funny thing. All these companies had this amazing new tech, but they also had a huge marketing problem on their hands. See, for years, they had been drilling it into customers' heads that more bits are better. So how do you suddenly turn around and convince people that your new 1-bit technology is actually better than the 16-bit systems they were used to?
Well, Philips launched a massive educational campaign to do just that. They had to teach the public that it wasn't just the raw bit count that mattered. It was the cleverness of the architecture, this new magic trick of noise shaping that made the real difference in sound quality. And you know what? It actually worked.
So, the crucial point here, the big takeaway, is that the legacy of Delta Sigma is so much bigger than just audio. It really represents a fundamental shift in how we solve engineering problems.
And this is the ultimate lesson. The success of this tech proved a powerful new design philosophy that we still rely on today. Whenever you're faced with a really hard analog problem, first ask yourself if there's a clever digital algorithm that can solve it for you instead.
You know, every single time you pick up your phone, there's this invisible battle raging inside. It's this crazy high-speed fight to manage energy. And today, we're gonna pull back the curtain on the unsung hero of engineering that honestly makes our entire mobile world tick.
For decades, right? The main problem has been super simple to say, but just incredibly hard to solve. The question is, how in the world do you power these super complex gadgets from a battery that has to fit in your pocket?
So yeah, that's really the big question we're diving into. How did we get from, say, those old pagers to the absolute supercomputers we carry around today? How did engineers figure out how to tame the beast, that raw power sitting inside the battery? All right, so let's rewind. Our story really kicks off in the early days of portable electronics. And the first solution they came up with, well, it was simple, I'll give it that, but it was also just shockingly wasteful. So this first attempt was a little thing called a linear regulator, or LDO for short. And you can think of it like a valve or a variable resistor. It would take all the juice from the battery, and then it would just burn off any extra power the chip didn't need. Literally, it would just turn it into heat. Wasted heat. I mean, the inefficiency was just staggering. Let's say your battery puts out 6 volts, but your phone's brain only needs 3 volts. Well, the LDO would just, poof, waste the other 3 volts as heat. That's 50% inefficiency. Think about that. Half of your battery's power was just gone, turned into heat, before it even did anything useful. And you know, for a little while, that was okay. But then, the 90s happened. Laptops started taking off, mobile phones began popping up everywhere, and all of a sudden, battery life became the critical feature. It was the #1 selling point. So wasting half your power? Yeah, that just wasn't gonna fly anymore. The industry needed a total game changer. And that revolution, it did come. It came from a completely different way of thinking about power. The idea was, what if power isn't a continuous river you have to dam up and let the rest burn off? What if it's more like tiny packets of energy that you can control and manage precisely? This new piece of tech was called the switching regulator. And here's the brilliant part. Instead of just burning away energy, it uses these components, inductors and capacitors, that basically act like tiny rechargeable batteries. They rapidly store and then release these little packets of energy, delivering exactly the voltage that's needed and nothing more. And the difference, it's just incredible. We're talking about going from this kind of clumsy brute force method that was at best 50% efficient to this really elegant solution that's 90, even 95% efficient. This right here, this was the leap. This is what made modern battery life possible. Okay, so efficiency was a huge win, but that was only half the battle, right? The next big problem was, how do you make this amazing tech small enough and cheap enough to put inside a phone for everybody? And to answer that, we have to talk about an absolute icon, Nokia.
So if you look at the timeline, it's pretty clear. In the 90s, the big enemy was just raw inefficiency. By the year 2000, Nokia was tackling the next big thing, integration. Then, of course, 2007, the iPhone shows up and introduces just a whole new level of complexity. And today? Well, today the big fight is against something a lot more subtle, electronic noise.
See, the engineers at Nokia looked at this and realized, hey, we can't have dozens of separate little power parts all over the circuit board. It's too big, too expensive. Their stroke of genius was to figure out how to combine all of those major power functions onto one single custom-made chip. And this chip, it was really the grandfather of what we now call a PMIC, a Power Management Integrated Circuit. And it did everything. It handled charging the battery, it supplied all the different voltages needed for different parts of the phone, it communicated with the main brain, the processor, and it even managed the whole power-up sequence when you turn the phone on.
And the result of this? It was huge. By squishing everything into one component, Nokia made phones that were super tough, way cheaper to build, and they had that legendary week-long battery life everyone remembers. This wasn't just some cool engineering trick, it was a massive business advantage that helped them just dominate the market. But of course, the story doesn't stop there, because in 2007, everything changed. The whole game was turned on its head, and the pressure on that little power chip, it just exploded into a whole new universe of complexity.
You guessed it, the iPhone arrived. And suddenly, a phone wasn't just for making calls. Now it was your camera. It was your GPS. It was a serious gaming machine and your music player, all crammed into one device. And every single one of those jobs needed its own specific amount of power, managed on the fly from moment to moment.
So the PMIC inside a modern smartphone is it's an absolute marvel. We're talking maybe 30 different regulators all packed in there, constantly talking to the main processor at incredible speeds. It's using this cool technique called dynamic voltage scaling, where it's adjusting power levels in millionths of a second. It's giving the processor just enough juice to do its job and not one single drop more. It has literally become the phone's energy brain.
And that brings us right up to today, and maybe the trickiest challenge of all. It's not just about being efficient with power anymore. Nope. The new frontier, the really tough problem, is dealing with electronic noise.
So here's the thing. When you switch power on and off millions of times a second, you create electrical interference. It's just physics. So the huge challenge for engineers now is how do you put this high-power system literally millimeters away from a super sensitive antenna for Wi-Fi or 5G? And, well, how do you prevent the power supply from jamming the radio? Because if you mess that up, you get dropped calls, your Wi-Fi gets glitchy. It's this incredibly delicate dance they have to perform.
This quote right here, it's pretty much the key to our whole story today. It's a huge idea that we're going to unpack, and it shows how pure ingenuity can find a way around what seems like an impossible physical wall. So hang on to that thought as we go. All right, so let's set the scene. We're back in the 1980s, the digital revolution is just hitting its stride, all thanks to Moore's Law and this thing called CMOS scaling. Now, that's basically just the process of making the tiny transistors on digital chips smaller and smaller and smaller. And while that was amazing for digital stuff, it created a massive problem for analog circuits. And this was the central question, right? As these digital chips kept shrinking, the amount of voltage they could handle also dropped. A lot. Now, for analog circuits, which need really precise voltage levels to represent real-world things like sound or radio waves, this was basically a death sentence. The big question on everyone's mind was, how on earth is analog supposed to keep up with this? But here's the thing. Analog designers didn't just give up. No way. They got incredibly creative. They invented a whole new survival toolkit to live in this new, low-voltage digital world. They came up with things like the folded Cascade to deal with those shrinking voltages. They made switched capacitor circuits, which was a super clever way to use digital parts to act like analog resistors that were suddenly impossible to build. And they used delta sigma modulation, a wild technique that basically traded raw digital speed for amazing analog precision. You see, they weren't just surviving, they were evolving. So by the late 1990s, analog had adapted brilliantly. It was holding its own in things like audio and power management. But there was this one final fortress, one challenge that seemed truly unconquerable: the radio frequency front end. We're talking about the actual part of your phone that communicates with a cell tower. The very idea of building a radio on a standard digital chip, what we now call RF CMOS, was considered an oxymoron by the entire industry.
I mean, it was literally a contradiction in terms. Why? Well, because everyone, and I mean everyone, believed that standard CMOS was just way too slow, way too noisy, and way too weak for the super high-frequency world of radio.
And this slide really lays out the standoff perfectly. The old way used these exotic, really expensive materials like gallium arsenide. It worked great, don't get me wrong, but it took multiple bulky chips to get the job done. The dream was to put the whole shebang on one single super cheap CMOS chip, but the physics seemed to say, no way. The big problem was the silicon itself. A digital chip is a really busy, noisy place. Think of it like trying to have a whispered conversation in the middle of a rock concert. That digital noise would just completely drown out the tiny, delicate radio signal.
So everyone thought it was impossible. But the dogma was about to be shattered. And the breakthrough didn't come from some fancy new material or a new kind of transistor. Nope. It came from a totally different way of thinking about the problem. And it was born in a university lab.
Specifically, the whole thing started with Professor Asad Abidi and his students at UCLA. They looked at what everyone in the industry believed, and they challenged it. They basically said, hey, what if we're looking at this all wrong? Yeah, maybe individual CMOS transistors are noisy, but what if you could manage that noise with a smarter system design?
Okay, so how'd they actually pull this off? The old way of building a radio, called a superheterodyne, needed this big, bulky, expensive filter that had to live off the main chip because you just couldn't build it in silicon. Abadi's team pushed for a new architecture called 0IF, and the key was it got rid of that impossible external filter completely. It just took the radio signal and converted it directly into its base information. And this is the genius of the whole thing. This was the core concept. Now, this new 0IF radio had its own set of problems, sure. Stuff like DC offsets and noise. But the solution was brilliant. Just use the massive, cheap digital horsepower that was already on the chip to constantly measure the analog circuit's flaws and then digitally erase them. So once this idea was out there, it set off an absolute gold rush in the commercial world. We're talking the early 2000s, and suddenly startups and industry giants were all racing to build the world's first true single-chip radio. They knew it would completely change the economics of every mobile device.
And here's pretty much how that race played out. What began as an academic project at UCLA in the 90s exploded into reality. By 2001, a company called Silicon Labs shipped the first ever all-CMOS transceiver for GSM phones. Right after that, Broadcom used these same ideas to create a single-chip Wi-Fi solution. And even the giant of the industry, Qualcomm, completely pivoted its strategy to this new architecture.
And you just can't overstate the impact. It was absolutely staggering. Silicon Labs proved this wasn't just some lab experiment, it could power mass-market Samsung phones. Broadcom made Wi-Fi so cheap that it became a standard feature in, well, everything. And Qualcomm used this integration to create the modern system-on-chip, the SoC, which is the single chip brain that powers practically every smartphone today. The oxymoron had become the reality.
Okay, so let's tie all of this back to today. This little history lesson isn't just a fun fact, it's literally the foundation of the mixed-signal marvels that we all carry around in our pockets every single day.
When you look inside a modern processor like an Apple A17 or a Snapdragon 8 Gen 3, that old separation between analog and digital, it's pretty much gone. They are a totally seamless blend of both worlds, built directly on the legacy of this RF CMOS revolution. And this gave birth to a whole new way of thinking, something called digitally assisted analog. The idea is, instead of trying to build physically perfect analog circuits, which is super expensive and hard, engineers now intentionally build small, fast, but imperfect ones. Then, they just use the chip's massive digital brain to constantly correct for all those little imperfections in real time.
I just love this quote because it captures the new relationship perfectly. The analog part of the chip basically acts like a sensor. It's out there gathering all the messy, real-world information. And then the digital brain takes all that raw data, cleans it up, and makes sense of it. They work together in perfect harmony.
So, you see that whole analog dilemma we started with? It wasn't a dead end, not even close. It was actually the catalyst. It was the pressure that forced this incredible revolution in thinking, which in turn created the chips that built our entire connected world.
And that brings us right back to where we started. The physics of silicon looked like an impenetrable wall. But by completely rethinking the problem, by changing the architecture, engineers built a bridge right over it. It's just a powerful reminder that even when you can't change the laws of physics, you can always change the design.